So the first video is to control the pin as outputs. So I added some resistors and 8 LEDs to the output ports of this device. So here I have my Python script and also my Python library, which is called the USB IO Expander, which provides all kind of functionality to make life easier. And this is the test pins output script that I created. So what you normally do, you import the required functions from the USB IO Expander, and each script has a main part in which it uses a default COM port, but if you provide arguments it will use that COM port, and then it will initialize the COM port. And then it starts with in this case with the pin functionality. So we start with setting all pins to output, we switch the pins low, and then there's an endless program in which we set all pins high, all pins low, and then each individual pin high and low. And each function returns true if the command was successful, and if it's false then you get an error message. So I will now run this program, and as you can see, the LEDs are turned on and off, and also the individual LEDs are turned on and off. And you can also see here what the program is doing. Using the control pins as input, and in this case I added pull-up resistors to the inputs because otherwise they're floating, and I'm using a wire which is connected to ground to make each pin low for a certain amount of time. So this is the test of the pins, but then we use them as inputs. So we start, all pins are connected to the VCC via a pull-up resistor. So first I'm setting the pin direction to input because of course I want to read the pins. And here I enable, there are 2 pins that have a weak pull-up resistors. I enable them, but it's not really needed because there are already pull-up resistors. Then there are 4 inputs that can be set to analog, so we need to set them to digital. These are pins 0, 1, 2, 3 and 6. And then we run the test. So first we get the status of all the pins by reading the port, and then we get the status of each individual pin, and this is repeated continuously. So let's run this one. So what you see is the port status FFFF because all pins are high, and now I will make each pin low individually. So I start with the least significant bit. Oops, so. And then the next one, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, and bit 7. And control an IO expander via I2C. So the USB IO expander is connected to a separate IO expander which can control 8 outputs or 8 inputs. And the communication is via I2C, so there are 2 pull-up resistors. The next demonstration is a demonstration of the I2C interface. So I have connected an 8-bit IO expander to this USB IO expander via I2C. So we start by initializing the I2C interface with a frequency of 400 kHz. Then on the IO expander I will set all pins to output. The next step is that I set all pins to high, so the LEDs will be turned on, and then I will set all pins to low. Then the program continues with an endless loop in which I will put one LED high or one pin high in the port register. I will read the value back from the latch register because you always should read back from the latch if you don't want to use the ports as input. And then the next LED will be turned on. When it reaches the end, then it goes the other way around. So I start with the most significant bit and move it back to the least significant bit. So let's run this program. controlling an IO expander via the SPI interface. This is a chip of the same family, but instead of the I2C interface it has an SPI interface. So this demonstration will show the functionality of the SPI interface. And you may wonder if you have a deja vu, because I have connected again an 8-bit IO expander to this USB IO expander, only now one with an SPI interface. So we start by initializing the SPI interface with a certain mode and clock, which you can find in the manual. And then we need a chip select pin. So one pin is needed to activate the device. So we have selected pin 3, which will be set to output and will be a digital pin. And then we can actually access the device by first selecting the device, writing some data, and then deselecting the device. And in this case we have set all pins to output. Then we will make all outputs high, all outputs low, and then the program continues as in the I2C program by making one pin high and moving it to the next pin. We will also read back the data that we have written, and when the most significant LED is on, we will turn it around and move it back to the least significant LED. So let's run this program. Controlling the ADC. For this I'm using a potentiometer which I connected to one of the analog inputs. When I change the position of the potentiometer, you will see the changing values on the screen. The next demo is the demonstration of the analog to digital converter. So we start by initializing the analog to digital converter with a selected channel. In this case it is channel 4. Then we will enable the ADC, and then we will show continuously the value of the ADC. And there is a potentiometer connected to the board, and I will turn the potentiometer so that you can see the change in the value. So let's run this program. So I will lower the voltage on the input, and I will make it higher to the maximum, and lower it again. Controlling the DUC. In this demo I'm writing different values to the DUC, and the output of the DUC is measured using a multimeter. The next test demonstrates the functionality of the digital to analog converter. So we start by initializing the DUC. The selected DUC is set to 1, so we're actually using the first digital to analog converter. Then we will enable the DUC, and then the following program continues. First is we're setting the DUC to the minimum value, then we're setting the DUC to the maximum value, and then we increase the DUC value from minimum to maximum in small steps. So you can see the results on the multimeter, and let's run this program. Controlling the PWM. In this demo I'm creating two PWM output signals with the same frequency but with different duty cycles, and the signal is shown on an oscilloscope. So this video shows the PWM functionality. I will initialize the two PWM outputs. So start with PWM1, PWM2, then I will enable both outputs, and then I will change the frequency on both outputs. The frequency on both channels is the same, but what you can change is the duty cycle. So we start with a minimum frequency of 750 Hz, and for channel 1 I will start with the lowest duty cycle and will increase until its maximum. And for channel 2 I will start at 100% duty cycle and will decrease until the lowest value. And after one round the frequency will increase with 250 Hz, and the maximum frequency is 45 kHz. So let's run this program. Of course this will take some time, but I can stop the program, and what you will see is that it keeps on running with the latest, let's say latest PWM frequency and duty cycle. So I will stop it, and still the signal is there.